Thank you very much. It's a pleasure to be here. And so I was asked to talk a little bit about four-manifolds, and I had no idea where to begin. So I decided to begin at the beginning. And don't take it as an insult, but I will just repeat a lot of stuff I'm sure many of you know, but let's just put things on a common ground. So manifolds. And if you create an X, you'll be always a topological space. And we say that it's a manifold if for every point there is an open neighborhood U, so and phi homeomorphism for some n. We all know that, and the usual picture is my manifold will always look like a Plato kind of thing. And we pick a point, there is a neighborhood, and a map phi, which identifies it with Rn. Okay, so these are the objects we would like to study. Definition: a smooth structure A is on X is a collection of such, and we call them charts, so that the transitions are smooth. So what do I mean by that? So we have a chart, and we have another chart around this X, the X, identification with Rn. Rn will be denoted by a box. And we take this intersection, and it appears twice. And by taking the map going back, and so using this psi and then phi, we get a transition function f. And the assumption is that we have a collection of charts which covers the manifold, and all these transitions are smooth. So as you all know, this allowed us to talk about differentiable functions. So if we take a function to R, then we can talk about differentiability at the point X by taking a chart, and by this property, it will be independent of the chosen chart. So that's fantastic. So A allows us to talk about differentiability. Even if we have two such gadgets, X1 and X2, equipped with two smooth structures, we can talk about the differentiability of this function f. You have to apply the chain rule twice, right? We pick a chart here, a chart there, and it will be independent of the chosen charts. Very good. And so we aim understand smooth structures. And the first question when we put out an aim, the first question should be why? Why do we want to do it? And I will give you two reasons. It took me a while to sort of understand why we do that. The first reason is that typical examples, say in other parts of mathematics or in physics, do come up with such as smooth structures, like this. The other reason is that it's very successful in the sense that once we fix a smooth structure, we can pull out a whole bunch of mathematics into topology to study manifolds, namely analysis. So for XA, we can use analysis in various forms. I'm sure there will be a little discussion about Morse theory. So, for example, studying the critical points of a function, which only makes sense if the function is differentiable, we can deduce all kinds of topological information about the manifold itself. And the probably the most famous success story in this in this question is the resolution of Poincaré's conjecture. If you have a free manifold, then it comes with a smooth structure. Using that smooth structure, people, Hamilton and Freedman, studied a specific PDE, and they used very solid topological consequences. Namely, they showed that if you have a closed free manifold which is simply connected, then it has to be homeomorphic to the standard sphere. So, e.g., Ricci flow in dimension 3. So this is my few-minute pitch of why do we have what we would like to study and why do we want to study this. So before turning to dimension 4, let me just list a few facts in other dimensions. So these are facts, and we will not talk about the proof or any indication. But so first of all, from now on, X will be always closed unless otherwise stated. So it's a compact n-dimensional manifold with empty boundary, and I will always assume that it's connected. Otherwise, we just study the components individually. So if the dimension of X is at most 3, then there is always a unique smooth structure. Unique up to diffeomorphism, which just means that there is a homeomorphism between the spaces which is differentiable in both directions. The existence part is actually used in the resolution of Poincaré's conjecture. If the dimension is at least 5, then there are at most finitely many. There are always finitely many distinct A's. So finite includes the number 0, so it can happen that a certain topological space which looks like a manifold does not admit any, or if it does, up to this equivalence of diffeomorphisms, there is always finite many. And another curious fact, and this will deviate a little bit from the closeness. So if X is homeomorphic, is smooth, homeomorphic to Rn, and n is not equal to 4, then X is diffeomorphic to Rn. So I'm sorry it's a little crambled, but so if you take these together, then you see that 4 is missing from the first 2 lines, and 4 is excluded in the last one. So there is something interesting happening in dimension 4. And let me just state what are other facts. We will be more concerned. Fact number 2, there are infinitely many four-manifolds with infinitely many distinct smooth structures. So this is in contrast with the uniqueness in lower dimensions and the finiteness in higher. There are uncountably many distinct smooth structures on R4. So that's as much of a contrast to the uniqueness as it can be. There are these set theoretic arguments saying that in a compact manifold, you can have at most countably infinitely many smooth structures, and this infinite in my language means countably infinite. And if it's not compact, it can support a continuum many, and this is exactly what happens for us. So you can see that there is a very drastic difference, and the analogy we usually use is that dimension 4 is somehow a phase transition. It's like when ice is melting, it becomes water, there are all kinds of interesting things happening at that particular moment, and this is dimension 4. This is how we sell this rational, other column. Not that we need it, but it's not that consistent. Okay, so why is it so special? Well, I will try to communicate that something strange happens in dimension 4, and there is one particular instance I would like to work a little bit more in detail. So consider the two copies of the three-dimensional sphere, and imagine them as unit quaternions. So we take S3 times S3, and there is a map into SO4 by taking the unit quaternion Q plus. So these are unit quaternions. And Q minus, and we send it to a function phi Q plus Q minus, which acts on a quaternion by conjugating in this sense. So there is a lot to check, but it's not very complicated. It's a little bit of playing around with quaternions to show that this is actually, if you take the two unit quaternions, this will be an element in SO4. And this is a 2-to-1 map. Obviously, 1, 1, and -1 will map to the same, the identity. And you have to convince yourself that this is a group homomorphism, and it's actually 2-to-1. Which means that the Lie algebra of SO4 actually splits. The group is not the direct product per se, but the universal cover is, and the Lie algebra only sees the universal cover. So this will be a sum of the Lie algebras of two copies of SO3. So this is the only dimension where this happens. The Lie SON is usually simple, but it does split in this particular dimension. So why is this relevant for us? Well, there is a little remark that lambda2 of Rn can be identified with the Lie algebra of SON. I have to remind you, like SON, these are the matrices which satisfy this identity. So the Lie algebra is just those matrices which satisfy this. So these anti-symmetric matrices. And if you have a matrix like this, you can send it to skew form omega, which is defined by this formula, where G is just some Riemannian metric on Rn. So this splitting splits lambda2 of Rn. And lambda2 is the space of two forms. This is relevant in differential geometry, namely, for example, lambda2 is where curvature lives. Of course, not for Rn, but for you have to globalize this trick, and so it makes sense to take a connection and demand its curvature to have one component vanish. So this splitting sort of refines a demand on the curvature. You can ask the curvature to vanish per se, which leads us to flat connections. But now we say that somehow we can talk about the positive and the negative part of the curvature, and we can ask this half of it to vanish. This only happens in dimension 4, and as you will see, this will lead to these PDEs, which will be very successful in studying smooth structures in four-dimensional manifolds. This is just a preview, and Tom, hopefully, will give all the details, or not, we will see. So this is my take on what to study, why to study, why is four dimensions so interesting, and what are the tools we will employ in studying them. And now we have to go back and sort of do a systematic understanding of four manifolds. So I will start with the algebraic topology. Four manifolds. So whenever you have a manifold or a topological space, the first question is fundamental group. This is, the name already suggests that you have to understand that. And here's a fact. For every finitely presentable presented group G, there is an X4. Again, I always assume that it is compact, no boundary, connected, and even you can assume that it's a smooth manifold such that I1 of X is isomorphic to G. And we do know that understanding groups in total, it's a very complicated problem. There is no algorithm to decide whether two presentations are isomorphic in general. And so there are various ways to get around it. For example, we can assume that study is connected. So pi1 equals 1 case. This is very restrictive in dimension 2. We know that there is only one closed two-dimensional manifold, it's the sphere. Now we know that it's very restrictive in dimension 3, because there is a unique manifold with that property, but it provides a very rich structure, very rich family of examples in dimension 4. So this is a rich source of examples. So I will mainly concentrate on that. Sometimes we will deviate from this, but this line suggests that to ask the classification problem in absolute generality, that's just too ambitious. Okay, so once we sort out the fundamental group, the next thing is homology. So H upper star and so the homologies and the cohomologies. We will concentrate on cohomology, as I hope you remember it from your algebraic topology class, that cohomology is a little better because this is not only a group, but it's a ring. So we take this as a ring. If we assume simple connectivity, then of course the first and the third cohomologies vanish. So the ring structure is sort of captured by one single map, which goes from the second to the fourth. And now we will assume a little more about our four manifolds. So from now on, assume that X is oriented. Notice that if we assume simple connectivity, the manifold is always orientable. And if I assume, as I always do, that it's connected, it has two orientations, and just pick one. And to pick an orientation is the same as to pick a generator or a fundamental class of H lower 4, or alternatively, yeah, that's good. Okay, so what is this map? And now we assume that we have an oriented, closed, connected four manifold. It says a pair of classes AB to A cup B, cups product, which then can be evaluated on the fundamental class. And so this can be identified with C, and we have a form on H upper 2 with integer values. And this is what's called the intersection form. Maybe I will spend a little time explaining why is it an intersection form and not a cup product form, but that's what we call it. Notice that QX is symmetric by the feature of the cup product. It's bilinear. And by contrary duality, it is unimodular, which just means in the simplest term is that in a basis, its determinant is plus or minus 1. So it's kind of an invertible matrix, invertible over the integers. Okay, so it's sort of a special symmetric bilinear form of a free group, right? This, if we assume simple connectivity, this is just z to the v2, the second Betti number of x. So these objects were studied quite well in algebra and in number theory. And here is a, I will get back to that, but let's do some examples. So the simplest closed connected four-manifold is just S4. These are those vectors in R5, which have only one. And the intersection form is just 0. It's the second cohomology is just a 0-dimensional or rank 0 free abelian group, and there is not much we can say about that. The next one is CP2, which is just complex lines in C3 through the origin, which is the same as we take the unit sphere in C3, which is just a 5-dimensional sphere, and divide out by the multiplication by complex numbers of unit length, or we can just say that these are these homogeneous coordinates x, y, z, x, y, z are in C, and this bracket means that they are determined up to a scalar, and it cannot happen that all three are equal to 0. Okay, so this is CP2. This is a complex manifold, and we have to remember that complex vector spaces come with a canonical orientation. Just pick a complex basis, and then you turn it into a real basis by taking vector I times vector, second vector I times second vector, and so on. And it turns out to be independent up to an even permutation of the order of the complex basis. So when I talk about CP2, I always think of the complex orientation, and actually this is a convention for every complex surface. So, okay, what's the intersection form? Well, we do know the cohomology ring of CP2, so H upward star is CP2Z is just Z is the generator where the cube is 0. And this is in degree 2, so it's a second homology element. So this will be just a 1-by-1 matrix, which is very much invertible. It's just 1. And this is a manifestation of saying that two complex lines, complex projective lines, intersect in one point on the complex projective plane. This sort of starts to justify the name intersection form. CP2 bar is the same four-manifold with opposite orientation. So its intersection form is a -1, since everything stays the same, the topological space stays the same, but we pick the other generator in age lower 4, so the evaluation will give you -1 instead of +1. Okay. S2 cross S2 or for the more complex oriented audience, CP1 for CP1. Oh, this is again a nice simply connected four-manifold, and the intersection form can be computed. So the second cohomology will be of rank 2. It will be a 2 by 2 matrix in some basis. And if you take the basis S2 cross a point and point cross S2, then the intersection form will be this 2 by 2 matrix. We usually refer to it as H, the hyperbolic pair. Okay, so this is again very simple algebraic topology. And finally, there's this infinite family of SD, and I just realized that I also call it S. This refers to sphere, and this S is surface. These will be complex surfaces. So these are those points, 4 tuples of points, points in CP3 which satisfy the following so it satisfies this homogeneous degree D polynomial. Whenever we write a homogeneous polynomial, this makes sense. The zero set makes sense in the projective space, and we take of degree D. And it needs a little bit of a thinking that this space is smooth. That's just the careful use of the implicit function theorem, which we all learn and teach and sometimes use. And it's a little harder to show that it's simply connected. And then to compute the intersection form, it's a longish exercise, which I will not do. I will just pick one particular value, which is of particular interest. So Q of S4, so when D is equal to 4, but don't be fooled. This is not because it's dimension 4. This 4 is for some other reason 4. This is just twice the E8 lattice plus 3 times the hyperbolic, and the E8 lattice, I hope we all know what it is, but just, this is the usual diagram. So this is the Dinkin graph. All vertices are frame -2. And then the corresponding intersection matrix is what I will call EA. The reason I was telling you that I'm using convention that there are all minuses here. Okay, so these are 4 manifolds, and then this is the bunch we would like to work with. So let me just go back to algebra a little bit and talk a bit about the intersection form. Right. So intersection form. So let's draw the manifold. Now we have an abstract symmetric bilinear form, which is unimodular, or a free rank D group. So this is symmetric bilinear unimodular. Just like an intersection form of four manifold, what can we say about that? So here is a theorem, and I will not give any argument for that. We'll just quote it. Sorry, I'll start with the definition. So Q is indefinite if there are xy in ZD such that Q of xx is negative and Q of yy is positive. Otherwise, I call it positive definite if all non-zero vectors have positive squaring distance, and negative definite they all have negative. And so it is the theorem. And I would have a hard time attributing it to someone, this is like a collection of common knowledge for quite some time. So here is the if Q is indefinite, then Q is isomorphic, or Q is some basis. Q can be written as, and there are two options. It's either a diagonal matrix, and the diagonal entries are plus ones or minus ones, which I will abbreviate by saying m times 1 and m times minus 1. So this is just 1, 1, minus 1, minus 1, all of zeros outside. Then we have n of those and m of those. Or for some number of E8s plus some number of the hyperbolic path. The distinction between the two is that in this case, Qxx is even for every x. And in this case, this is not true. Of course, you take the first vector, and this has Qxx1, so this is an odd number. So these guys are called odd, and these are even symmetry values. Okay, so the upshot is that if you have a symmetry bilinear form which happens to be indefinite, then the classification is quite easy. You can characterize them by two numbers, how many ones and how many minus ones, or how many E8s and how many Ls, plus whether it's odd or even. So these are three pieces of information, two numbers and one arithmetic profit. Okay. If Q is definite, and I will not forget the theorem, it's just is. So, for example, I did read that, and I hope it's true. For rank 40, there are 10 to the 80 such different, or roughly 10 to the 80 such different intersection forms. This is like, I don't know the number of atoms in the universe or something like that, but we can't handle that. So this is complicated. The indefinite case is pretty much, you can keep it under control. Okay. So why are we so hooked on the intersecting form? Is this famous theorem of Freedman, 82, saying that suppose x1, x2 are two simply connected smooth four-manifolds. Then x1 and x2 are homeomorphic if and only their topology rings are isomorphic. So this is a ring isomorphism, which is just the same as to say that the intersection forms. This is the only information from the ring structure after the assumed simple connectivity. So the intersection forms are isomorphic. Okay, so this is one theorem from that theorem. This shows that an active union for dimensional topology, as we'll see. The next theorem is Donaldson. Again, 82. If X is smooth, and Qx is negative definite, then Qx is isomorphic to the diagonal form. So this is remember, this is just O minus plus in diagonal and 0 outside. So there are many different definite forms in number theory, but as an intersection form of smooth four-manifolds, there is only one negative definite, and it has its counterpart, one positive definite appears, namely the diagonals. Maybe this theorem will be proved, I don't know. Maybe. Let's reassure you. So it's worth coming, right? Maybe not. Make it clear. So this is a beautiful theorem, quite unexpected, and this gives a corollary, which will be very useful in our subsequent discussions. So x1, x2, smooth four-manifolds. And again, I assume simply connected are homeomorphic. If I go leave, they have the same line characteristic. They have the same signature. And I didn't define the signature, so I will just remind you, but I hope you sort of remember that this is just the difference between the maximal positive definite and the maximal negative definite subspaces in our Freedman group, and same parity. So this means that in order to check for smooth four-manifolds homeomorphism, whether they are topologically the same, is a reasonably easy exercise, provided you believe the two theorems, which are not so easy exercises, that we have to check two numerical invariants, the Euler characteristic and the signature, and the mod 2 invariant, the parity of the intersection form. These are very easy to compute when we will do the manipulations we are planning to do, namely cut manifolds into pieces and reglue them, because these two are additive, and this is just a nuisance, and we can ignore it, but it's sort of a fun little exercise to actually follow what happens. I should remind you that evenness of the intersection form of a four-manifold in the simply connected case refers to the spinness of the four-manifold. So it also has some deep geometric meaning, and odd is not. Okay. So I should pause for a second. So this is not really what Freedman proved. This is a consequence of what Freedman proved. He proved way more. Actually, he showed that forget about smoothness. This holds with a little bit of a modification for topological four-manifolds, and indeed, every intersection form can be realized as every symmetric bilinear unimodular form can be realized as an intersection form of a topological form. So the chaos holds for topological four-manifolds, but Donaldson made order in the smooth case and selected two types which do admit a smooth structure. And it also shows that there are many topological four-manifolds which do not admit any smooth. Okay. So this theorem just tells us that if we would like to create topological manifolds with many distinct smooth structures, and this will be one of the goals of this lecture series, then what we should do, or what we can do, is to cut and paste manifolds in all kinds of ways, and hopefully get different smooth manifolds. And to check whether they are homeomorphic, you just have to follow what happens with these three invariants, and then apply the corollary of this two-base theorem. So this tells us how to decide whether two manifolds are homeomorphic or not. But there is still a question which Q can be realized as QX of a smooth four-manifold. So these theorems just tell us what happened, how to relate the two, but when can we realize them? And here is a little of observation. So if we have x1 and x2, then we can form the connected sum, which is just to puncture both, to take out an open neighborhood of a point from each, and glue together the resulting S3 boundaries. Luckily, we do understand how many different maps between S3s, between two copies of S3s exist, especially if we demand orientation reversal. Up to isotopy, there is only one. So this is a well-defined operation of oriented manifolds. And we always assume that our manifolds from now on, that they are oriented. So we can do that. And what happens with the intersection form? And it's not very hard to see that they will just sum, by which I mean that it will be a matrix where we copy QX1 on the upper left corner and QX2 in the lower right, and that's the new matrix. This is again very simple algebraic topology, and I will not spend much time on that. But notice that this immediately tells us that what happens with the odd intersection forms. So Q indefinite odd. So it's the same as n times 1 plus n times minus 1. Then we just go to this very limited inventory of manifolds and we pick a couple of CP2s and a couple of CP2 bars. Then Q is the same as Q of n CP2 connected sum n CP2 bar. So these can all be realized. Now, among definites, we have Donaldson's theorem that only the diagonal ones can appear, and of course, Q definite. Then Q can be the intersection form of some copies of CP2, or if it is negative or negative definite, then M copies of CP2. So whenever we have a chance by Donaldson's theorem, we can live with that chance and they are really realized. What happens if Q is indefinite and even? So we know from this theorem that it should look like K times EA plus N times H. Now there are two observations. The first is that there's a theorem of Rocklin, which says that if we have a simplical R, so if we have a spin manifold, spin four-manifold, which is smooth, then the signature should be divisible by 16. Let's see what is the signature here. So H is just this matrix, and it takes a little bit of a thinking that it has both elements of positive and negative squares. So the signature should be 0. So the signature is 0 here. The signature is -8 for the E8 matrix. So altogether, the signature is -8K. But now Rocklin comes in and he says that if Q happens to be the intersection form of a smooth four-manifold, then the signature should be divisible by 16, which just means that K should be even. So Rocklin A is to S, as it should be an even number. Okay, so now we define our search. We take 2S EA plus L times H. Well, there is one guy which has this intersection form. So we take S copies of S4. That's a very unfortunate notation. So S4 is also known as the K3 surface. There are various theories why is it the K3 surface. So there are three mathematicians which I might not be able to list. It's Kumar, Kodaira, and Taylor. I don't know, maybe. And there is the other school who says that, well, there is this peak in the Himalayas, the K2, but this guy is much harder than that. So this is why it's K3. Anyway, we take S copies of the K3. So this gives us 2S times EA plus a couple of pages plus L minus 3AS age, provided, sorry, S2 plus S2, provided L is at least 3S, right? So that's a fantastic four-manifold, some, and we realize those. But there is this annoying assumption, whether it's needed or not, and in the theorem, if Qs EA plus L8 is the intersection form of F smooth four-manifold, symplective, then L is at least 2S. So this is the theorem of Ruta from 96, I guess. And it runs under the name of Penny theorem. And I will not explain why 10A. If you rewrite this inequality in terms of finite characteristic, second Betti number, and signature, then in the formula you will see a 10. And the conjecture is that, so first of all, this theorem has been improved by 10A plus an epsilon. Every now and then you can add a few numbers, 1, 2, 3, 4. I'm not sure whether we will talk about that later. We will. Someone. Okay, very good. So we will hear a little more about this and maybe even the improvement. But here's a conjecture, and this runs under the name of Penny-Elevate conjecture, saying that L is in fact at least 3S. So this piece, this is the last puzzle to understand which intersection forms can be realized as intersection forms of smooth, simply connected four-manifolds, because once this is satisfied, here are my examples. This is a hard theorem, and we will see sort of the limitations, hopefully, of the proof giving the Penny. Okay. So this is what I planned for the first lecture. I have a few more minutes, so all right, it's a 16 Okay, so let's start by saying that. So this is what we know about the algebraic topology of four-manifolds, and when we talk about homeomorphism type for simply connected ones, I will always jump back and forth between talking the homeomorphisms or these numerical invariants. But our ultimate goal is to create homeomorphic but not diffeomorphic manifolds. So we do need some way to distinguish homeomorphic guys. And so this is where Seiberg-Witten invariants will come in. We will write down, I will write down E, and it will be natural enough to show that if two manifolds have a different number of solutions for this particular PDE, then you can make sure that they are not diffeomorphic. This is what we need. It's easy to say. It's a little harder to sort of realize it because the most obvious PDEs, for example, consider closed forms or closed forms modulo exact forms. These are fantastic PDEs and they give you topological invariants, or you just can take a Laplace. And this will give you something to find. It will require the choice of a metric, and it will tell us something about the metric itself. So to see something halfway through is a complicated matter. This is what Tom will talk about, but I will just sort of summarize what the topologist takes out of that. So at the end of the day, we will have a function, which I will call Seiberg-Witten of X, which will be defined as the second cohomology of X. This is exactly where the intersection form lives, and this will be an integer value function, and with the properties the support of Seiberg-Witten is finite. So there are only finitely many cohomology classes for which this is non-zero, which already is great because we can take as an invariant just the number of those cohomology classes when it is non-zero. Well, it is defined or well defined if B2 plus, so the maximal dimension of the intersection form where it is positive definite should be bigger than 1. So it does not work for every four-manifold in such a nice way. And if F is a diffeomorphism, then Seiberg-Witten of X2 on a cohomology class K is just plus or minus the Seiberg-Witten of X1 on F upper star K. Okay, so in this sense, it's a diffeomorphism invariant. For example, the support is a diffeomorphism invariant. The cardinality of the support is a diffeomorphism invariant. And one more property, which I will just write over there. And this is a symmetry. Seiberg-Witten of X on minus K is again up to sign the same as Seiberg-Witten of K. So these are some of the properties we will use. There will be one more, which will be two more, which will be very important. But let me just give a definition. K is a Seiberg-Witten basic class if the value of the function is not zero. Okay. So these are the cohomology classes which somehow attach to the smooth structure. And I think it will be the way Tom will present it, it will be a little more refined. Instead of second cohomologies, these will be somehow substituted with the spin C structures of X, but I will leave him to explain what these things are. Okay. And here is a theorem, and I'm sure these will be, or some of these steps will be proved. So if B2 plus of X minus B1 of X plus 1 is odd, then Seiberg-Witten of X is constant 0. So this immediately shows that the invariants themselves have quite some limitations. You know, for some, this quantity for a manifold is either even or odd, as we all know. And so, yeah, I know it's deep, but that's how it works. So half of the manifolds are somehow excluded from this story at the beginning. So this shows some kind of limitations. We'll see how to overcome it every now and then with special tricks, but this shows that we are not at the end of the story. If X is a collected sum of two four-manifolds and V2 plus of Xi are both positive, so this is positive, then Seiberg-Witten of X is identically zero. That's again not very encouraging, having two results. We say that then we could just define the function to be constant zero. But the thing is much better. And this is the last thing I would like to tell you today. If X admits a two-form omega such that it is closed and non-degenerate, so the four form we get it this way is always positive, so omega is a symplectic form, then there is a cohomology class such that the Seiberg-Witten of X is plus or minus 1. So vanishing, non-vanishing. So there is something into this theory, and well, we will make use of these properties very much in trying to create homeomorphic but not diffeomorphic manifolds, and this will happen probably tomorrow. Okay, so this is where I would like to start today. Thank you.